Hello, my name is Marco Lisi. I work for the European Space Agency. Today I will speak about the satellite link budget. So far we have considered only free space losses, but there is at least one other very important contribution to losses. There are many others, but one important and non-negligible, surely non-negligible contribution to the losses experienced specifically from a satellite to ground and vice versa comes from the atmospheric losses. The atmosphere, let's say, or the travel of the electromagnetic wave from satellite to the Earth station, for a large part of it is outside the atmosphere, and there only the free space losses have to be considered. But when the traveling wave gets into the atmosphere, there is an addition of several contributions that attenuates the signal. Some attenuation comes from the ice that you can find in the very high layers of the atmosphere. Then another absorption, that is in fact an attenuation, comes from the oxygen in the atmosphere or the water vapor in the atmosphere itself. In the slide, let's say I have shown it as a cloud. Okay, it's in a cloud. You have water vapor that is absorbing again and attenuating, introducing losses in your link. But then another very important contribution is from rain and snow. So both rain and snow are attenuating heavily the RF signal, especially at microwave frequencies, and introducing a loss that can be calculated. We'll have a look at the different ways to calculate or to take it into account. And so, as a conclusion, we should, to be more precise, in the freeze formula that we have so far analyzed, that was only based on geometrical type of consideration and problems, we have to introduce these physical effects coming from the atmosphere with another loss or another contribution of losses that we call L sub A, mostly deriving from rain, but not only. So the total loss in our link then from now on will be in fact the sum at least of two factors, L sub P, that is the free space path loss, plus L sub A, that is the atmospheric loss. About atmospheric losses, you can find in literature thousands, literally thousands of papers, books, and studies. There are hundreds, if not thousands, of researchers and engineers working continuously to derive good models to take into account the losses deriving from the atmosphere, and in particular from rain. First of all, I like to here with this slide to show that this attenuation, and we are looking here specifically to the rain attenuation, depends very much on the type of rain. Type of rain in this graph is defined as millimeters of rain per hour, which is a characteristic way to define how heavy is rain used by meteorologists. So the higher is the rate, or the heavier is the rain, and intuitively it's obvious that the attenuation will increase. But also depends on the path that the signal, let's say the electromagnetic wave, is experiencing rain. And this will depend on the layer of the atmosphere that is affected by the rain, and also by the geometrical characteristics of the link itself. So for instance, if the geometry satellite to user station is giving a very slanted range, it's obvious that you travel through an area experiencing rain more. So a way to specify the attenuation from rain is dB over kilometers, just to take into account the fact that you might experience this attenuation for a longer or shorter distance depending on the geometry and depending on the type of rain. Rain coming from clouds at higher altitude would create a higher attenuation than the rain coming from clouds at a lower altitude in a first approximation. Then it's very important, and it's obvious from this graph, that the rain attenuation depends on the frequency of operation. So let's have a look. If I take the same rain rate, so the same number of millimeters of rain per hour, if I am at C-band, here I'm looking at a specific rain rate of, just to make an example, of 25 millimeters per hour. It's just one value to make a comparison. At C-band, this rain rate would give me an attenuation in the order of less than 0.1 dBs per kilometer, so it's very, very small. At Ku band, so C-band, we are speaking about 4 to 6 gigahertz, depending if you are in downlink or uplink. If we are at Ku band, so around 12 to 14 gigahertz, with the same rain rate, you experience a loss in the order of 1 dB per kilometer. But if you go now to Ka band, that means 20, 30 gigahertz, the attenuation goes up to 5 dBs per kilometer. So the two extremes, Ka band 5 dBs per kilometer, C band less than 0.1 dB per kilometer. By the way, C band is the least affected by rain attenuation, and that's the reason why C band is very dear to countries in the tropical areas and the equatorial areas, because those countries experience very heavy rains. Their climate is very humid and the rain is very frequent. So the only way to establish a link with satellite with low values of attenuation, so the ideal frequency of operation, is in fact C-band. Other frequencies would experience a non-negligible, in some cases substantial loss. Ka-band in tropical areas and equatorial areas is not forbidden, but it's surely much more challenging. And you find in literature many ways, many models to calculate this rain attenuation, to consider the effect of rain attenuation. So you get these maps, statistical maps, that give you the probability of a certain rain in terms of millimeters per hour over time, and the regions are defined with the letters, so you have better regions, lower regions. These are all definitions, and you can find a lot of information in literature and on the web. I like here to underline the fact that in a communication link, the approach is always somehow statistical, because in fact you cannot guarantee something for sure in all conditions. So you see from this slide and from the table that I have to define a certain probability of attenuation being higher than. If I look at the rainfall rate in millimeters per hour, I can define it in terms of 99.9% probability, which means that it will be lower than a certain value. So the attenuation, the corresponding attenuation, will be lower than a certain corresponding value for most of the time, but for 8 hours per year, that is corresponding to the 99.9% probability, it will be higher. If I define instead the probability as 99.999, then this duration through which the attenuation coming from rain is higher than a certain value, is going to be only 5 minutes per year. So what is the conclusion? The conclusion is it depends very much on the mission. It depends very much on the quality of service you want to deliver. Can I afford to lose my link 8 hours per year? That will happen statistically. It will be maybe 1 hour one day, 2 hours another day. Let's say statistically I should expect for no more than 8 hours per year my link would be fine, and only for those cumulative 8 hours per year I might have bad problems, because in fact I have defined the threshold. Probably above this threshold I would experience maybe the disruption of the link. Can I afford it? Are the 8 hours per year acceptable? Well, it depends very much on the mission. There are some applications where I cannot afford it. I cannot afford to have hours of disruption. So maybe the 5 minutes per year of the other table, that is much more conservative, are compulsory, which means that I have to consider into my link budget a much higher attenuation coming from rain, which means that I have to size my link on both ends, transmit and receive ends, to cope with this higher attenuation. So I have maybe to transmit higher power from the satellite, I have to get more gain from the satellite antenna, I have to have a larger antenna on the receive end on ground, and maybe I have to get better low noise amplifiers in my receiving chain on ground, just to cope with this higher attenuation in the link. Now we know how to get the receive power, so we know how this receive power will be affected by higher attenuation. So again, it depends very much on the type of service, and it has to be considered also what I pay for it. And if I can afford it, if it is physically achievable, let's say, given the terms of the problem, and if the service, the quality of service is going to be too much affected or not. So this is a sort of statistical view. Something similar we'll find later when we speak about the bit error rate. Again, in digital communications, we cannot dream about a transmission that is errorless. We know that we are going to experience, even in the best designed link, some problems in the link itself, which will result into losses of information in terms of errors in the information. I can counteract these problems, but I cannot eliminate completely my errors. So at the end of the day, I want to know what is the probability of experiencing a certain number of errors in my transmission. So you see that at the end, I anticipated that at the end of our definition of the link budget, in fact, we will have to take into account statistical approach for the link availability and also a probability of error. And depending on these two factors that are, if you want, both statistical, I will dimension then my link. So there is no single answer to the problem, but there is always a trade-off to be done in terms of availability, number of errors, and the other parameters that are affecting the link.